Just about 1 minute to go until we actually start up. Okay, it's time. I'm going to get rolling here. I'm hoping everything you're getting. I'm hoping you're getting my audio clearly. You notice I started up a little differently today. I decided to turn my camera off, and so that I could start sharing right in the beginning. Because when I started sharing, that's when I had my difficulties in the past. I still had to restart, but at least you guys didn't have to wait for me this time. So anyway, here we are, Trig 9. So I'm going to open it up. So if you want to ask me a question, just go ahead and speak up, or use the chat, the group chat. Remember, top left corner, there's that blue background with white writing on it. That'll activate the little chat box on the right. Or you can send me text messages. I've got my phone ready to receive. Did anybody have any questions you want to begin with from last time? Or one of those old quizzes? All right, well, then I'm going to get started. Trig 9, this will be our last new material. Tomorrow, Friday, we will dig into we'll start reviewing the semester. Okay. Well, we started talking about, and we started working on trigonometric identities. Remember, an identity is an equation that works no matter what you plug in for the variable. And I was a little bit on the, I don't know if I'd call it lazy, but I was trying to save a little time by not putting the variables up yesterday. So I said, like, for example, cotangent equals cosine over sine, whereas I really should have said cotangent of theta equals cosine of theta over sine of theta. So, but anyway, no matter what the variable is, except for some undefineds here and there. Oh, I do have a question. Okay, came by text message. Let me try to pull it up. Identities again, yeah. So actually what you asked me, I was in the middle of going through, but let me skip ahead, and I've got a slide that, just a minute, I got to find it. Yeah, so this is, I should turn those pictures off on the bottom so you guys can, so we can see more. Okay, should be able to see the screen a little bit better now. So these are the 8 identities that we have already been discussing. Identities, once again, are equations that are true no matter what the variable theta is. So no matter, I mean, except that, for example, if the sine of theta is 0, and where does that happen? It happens when what? We're at 0 degrees or 180, or any multiple of those. Then the cosecant, which is the reciprocal of that, of course, can't be done, because you can't take the cosecant. You can't take the reciprocal of 0. But, I mean, except for those undefined situations, these things are always true. So if you want to know the cotangent of 30 degrees, you can just take the tangent of 30 degrees and take its reciprocal. It'll work every time. Or if you know the sine and you want the cosecant, just take the value of the sine. For example, 30. What's the sine of 30 degrees? Or pi over 6. It should be 1/2. And so therefore, what's the cosecant of 30 degrees? The reciprocal of 1/2, which is 2/1, or just plain 2. So Beautiful thing about identities is they always work. It's also true of the three in the center of the page. Those are called what? The Pythagorean identities, because I showed you how they actually are what? The legs and hypotenuse of famous right triangles. So maybe I should, I don't know if we ever demonstrated this. I think we did. Yeah, we did. But let's just do it real quickly here. I'll change my pen color. Let's change to a blue. Let me get my keyboard out of the way here. I always regret that later, but that's okay. So, turn my power upside down so it doesn't get pinched. Okay, so let's just say for a minute that theta is 30 degrees. If theta is 30 degrees, let's go through this top. Hi, Matt. We'll go through this top. Yes, what did you say? Okay, I got partial voice from somebody. But anyway, let's take the top Pythagorean identity and check it out with 30 degrees. Okay, what's the sine of 30 degrees? 1/2. So what's the sine squared of 30 degrees? I'll just write it this way right now. 1/2 squared. Plus, what's the cosine of 30 degrees? Square root of 3/2. And it's cosine squared, so we're going to take that and square it. And that's supposed to always equal 1. Well, 1/2 squared is 1/4. And when you square this, the top, the square root of 3 squared is 3, and the bottom squared is 4. And you can see it works. It's equal to 1. And no matter what angle you pick, that'll always work. Maybe we should do just one more just to demonstrate. So let me, no, I can't. Let's see. Can I? No. So I'll just use the eraser here. Okay, and this time, let's use a different angle. All right, so, I don't know, should we take 45 degrees? Okay, what's the sine of 45? Opposite over hypotenuse, it's going to be what? 1 over the square root of 2. That's the sine of 45, and then, of course, like this says right here, we have to square it. What's the cosine of 45 degrees? It's also 1 over the square root of 2. And again, it's squared. And that's supposed to equal 1. I should really put a question mark. We don't know. We're going to try to prove that. 1 over square root of 2 squared is 1/2. Yeah, so both. And again, you can see it works. And what I'm telling you is it'll always work, unless there's an undefined value in there. So an identity is an equation. It's a law because it just always works. All right. So there's 3 of those. The sine squared plus cosine squared equals 1. The tangent squared plus 1 equals the secant squared. And the cotangent squared plus 1 equals the cosecant squared. And then these 2 on the bottom, I believe I introduced to you last time. Those always work too. So those are our 8 basic identities. Whoever asked me that question, I got to just check. Did I get another one? Yeah, it looks like that's the question I got via text message. So I think I've answered that question. Anybody else have a question? So I'm going to go back to the beginning here then. Hi, Brandon. Welcome. So trig 9, and we're going to, the question that was asked a few moments ago, go through identities. That's what we're going to be spending time on pretty much all day. I mean, all class. And maybe for the first time, we'll actually prove some new identities that we've never seen. So let's get started on one. So here is an identity that most likely you've never seen before. The secant of theta minus 1 over 1 minus the cosine of theta is always equal to the secant of theta, supposedly. Now, to prove an identity, we have to use those 8 basic identities we were just talking about in order to demonstrate that one side of the equation really is the same as the other side. And to do it correctly, you have to choose one side to work on and not touch the other side. And you usually want to pick the side that's more complex. Like on this one, it's the left side of the equation. Just one function, so that's obviously simpler. So we're going to kind of leave the right side untouched. And on the left side, we're going to see what we can do to work on that using identities. Okay, so for this first one, instead of doing it live, I'm just going to show you some steps. So one way to get started on this is, as long as the right side of the equation is only in one function secant, one approach is, can't we just change everything to secant on the left? Well, the top is already set. Is there a way to change cosine into secant? And there is, because isn't cosine just the reciprocal of the secant? So do you see what I did in this first step is I substituted in a 1 over secant to replace the cosine that was in the original statement. All right, now at least we have the left side all in secants. And we can still do more with that denominator. 1 minus 1 over secant. Wouldn't it be nice if I could get a common denominator and get that into one fraction on the bottom? And so that's what I do next. I say, well, 1 is the same as 1 over 1, right? And let me explain. So let me go back to blue for my writing again. So I need a common denominator right here to bring these two together. Can't I just multiply this denominator by secant theta, and of course, to make it legal, I multiply the top and the bottom by the same thing. Now, I skipped a step there, but I don't know if you can see what's going on. Now, do you see I have a common denominator for these two subtracted fractions on the bottom? And so that denominator now becomes secant theta minus 1 over secant theta. All right, so I did a couple. So let me fill in the blanks here. So that we didn't touch. That's the numerator up on top. But I just figured out that this bottom down here is secant theta minus 1 over secant theta. Why? Because I now have this common denominator. Okay, and then what happens when you divide one fraction by the other? This is like secant theta minus 1 over 1 divided by this fraction on the bottom. And so I invert and multiply secant theta over secant theta minus 1. And by the way, this is all left-hand stuff. I just ran out of space. It looks like I'm messing with the right side. I'm not. Well, what's going to happen here? The secant theta minus 1s cancel, and you get secant theta. And so the bottom line is, we just showed that the left side comes out to secant theta. And so, sure enough, secant theta on the left equals the secant theta that we had on the right. We have just proven that this is another identity. This thing right here, because we just proved the left side has to turn out to the right side, is a new identity. No, I'm not going to make you memorize it. And by the way, you'd never get them all because there's basically an infinite number of identities. But what is important is mostly what I did here. There's two things needed to prove identities. You have to know your 8 basic identities really well, and you have to be good at algebraic manipulations. So we've proven one. Let's try another one. Get my arrow, if I can find it here. Where's my cursor? Here we go. So here's another problem. 1 over secant x times tangent x equals cosecant x minus sine x. Okay, now this one is a little bit hard to determine which side is more complex than the other. I believe I'm going to be working on the left, and the main reason is because that stuff is all in the denominator. Yeah, I started by working on the left. Now, right now, I don't see an immediate connection between secant and tangent being multiplied and cosecant being subtracting the sine of x from it. So when you don't know what you're doing, one thing you can do is turn everything on the side you're going to work on into either sine and or cosine. Okay, so secant, can we turn that into cosine? Yeah, that's 1 over cosine. Tangent, can we turn that into anything sine, cosine? Oh yeah, that's sine over cosine. So do you get, so that's the mentality. So the first step is, in place of the secant, let's put its reciprocal in, 1 over cosine. And in place of the tangent, let's put its ratio identity component, sine over cosine. All right, hopefully that you caught on to that pretty quickly. That's important from last class. And then, let's see if we can follow what I did here. So if you multiply this denominator out, what do you get? 1 times sine is sine, cosine times cosine is cosine squared. So all I did was combine these two and multiply them to get that. I didn't touch the numerator of 1. Okay, now, what's this 1 over sine over cosine squared? Well, doesn't that just mean do the reciprocal? So as we scroll down here, what we are finding out is that if we just flip that sine over cosine squared, we don't need the 1 on top anymore. It just comes down to that. Now, so now we're at cosine squared x over sine x. Now remember, and this is the bad news of doing this electronically and not on a board. Let's go back. What are we aiming for? Oh yeah, we want to get cosecant minus sine. Cosecant minus sine. All right. Well, what can we do? Well, all right. I don't know if you see this. There's an identity, or at least part of an identity up here. Cosine squared. Do you remember the Pythagorean identity? Sine squared plus cosine squared equals 1. So if you manipulated that sine squared plus cosine squared equals 1 and subtract sine squared from both sides, cosine squared is the same as 1 minus sine squared. So do you see I made that substitution right here? All right. Believe it or not, that's helpful. Now, this step you might not get what I'm doing, so let me try to explain. Hopefully you can still all see that on the bottom. I actually degenerated this fraction and broke it up into 2 separate fractions, both over the common denominator of sine x. So 1 over sine x minus sine squared over sine x. So this is like kind of going backwards from a common denominator. Almost like a backward step. Do you see why I did it? Look, what is this? What's the reciprocal of the sine? Cosecant. Ah, that's what I wanted for my first term. Beautiful. And what's this? Well, what happens if you take anything squared over itself to the first power? Oh, it's itself to the first power. Look at that. That's exactly... Let me just go back up. That's what we were aiming for. We did it. We proved this identity. So again, not something to memorize, but now you know we just have gained this new identity up here on the top. And of course, like I was trying to hint to you, there's an infinite number of these crazy things. So it's not a matter of memorizing. We're going to just stay with our 8 basic ones that I had on the board last time. But we've just proven, hey, this sweetheart is always true. Therefore, we can now call it an identity. And we proved it. So I'm trying to give you a little bit of a taste here into how we can use these basic identities to prove more. Okay? Anybody, I should give you guys a chance to speak up. Okay, I do have a question here on the chat. I'm confused with all the secants on one side and then all the secants in the bottom. Okay, is that from this one or another one? Sorry, I can't always keep my head over at the chat room while I'm teaching. The other one. The other one. You mean the previous problem? Okay. So she's talking about this. Let's see if I can get this question. I am confused with all the secants on one side and then all the secants in the bottom. Wow, it's pretty hard to answer that one. I don't know exactly what you mean. I mean, there's at which stage of the game. I think what we might, it's just really tough to put together what you're asking. And I don't mean that this is not on you, Kirsten. It just, your question could mean about 20 things. So I think we're going to just have to talk about it. And we can do it in class because I'd be happy to. I know I can explain it if I knew what you were asking me. And obviously I went too quickly before because I've already tried to explain. But either in class or I don't know if we can meet outside of class, either one. Can you re-explain the problem? All right, I will. Let me just go over 18 one more time. I will do that. Thank you. So here we go. So the original problem is up there at the top in the box. We're supposed to prove that thing in the box. You want to work on the side that's more complicated. So that's this left side here. I know it looks like I worked on the right, but this blue stuff over here on the right that I'm highlighting right now, this stuff was, I didn't have room. That actually belongs over here. I was just showing you more detail. Okay, I didn't touch the right side. So what did I do over here? Step one, in this problem, I noticed there was only a secant on my answer side. So wouldn't it be cool if I could change everything to secant only on the left? And the only one that wasn't secant was this cosine that's on the bottom here. Okay, well, what's a nice substitution for cosine? Oh, yeah, it's 1 over the secant. And so in this red circle, I replaced cosine with the fact that it's the reciprocal of the secant. That was step one. Now, step two, I had this 1 minus 1 over the secant, this part right here. I know I got marks everywhere. But this thing in the blue box that I just drew in, that's our next task. How can I combine those two? Well, if I got a common denominator, I could. Well, this 1 is really what? Isn't that just 1 over 1? And so to make it have the common denominator of secant, I multiplied top and bottom by secant. So now it became 1 over secant minus 1 over, I'm sorry, it became secant over secant minus 1 over secant. And combined, you know, I don't know, okay, I can't go over how to make common denominators again, but that's what I'm trying to show you is I just made a common denominator and then I could bring those together and I shouldn't have circled that much. Let me undo that. What that allowed me to do then was, I mean, if you take these two fractions on the bottom and combine them, you get what I just circled in red. So all I did was combine the two common, the fact that I could now subtract them because we had the common denominator of a secant. So the top is the same, and now I've got this combined bottom. Now I've got the top divided by the bottom. That's the same as the top times the reciprocal of the bottom. You know, the old, how do you divide fractions? And multiply. And that's what I did up here at the right. Yeah, it's still hard to do. At least I tried. And if we need to go through it again tomorrow, I will. Yeah, we're a little bit too confined for me to show you everything, but I'll do my best. Thank you for asking. So as we cut this little time out here, is there any other question I can meet? All we've done is 2. I want to go on and do at least probably a couple more. All right, I'm gonna move on. Let's see now. Well, where were we? Okay, we just finished that one. So, yeah. Let me clean this up a little bit. I'm going to do some erasing so I can write in a different color so things will be a little clearer. So I'm going to erase what I multiplied by. Here was the original problem right here. So this again, on the very top there, that's what we're supposed to prove, this thing up here. That's the problem. Can you show me that the left side will always equal the right side? That's basically what it's telling me. Well, obviously, the left side is the more complex side, correct? I mean, it's got 2 rather ugly-looking fractions. At least on the right, we only have 1 function. We got a 2 in there. So it should be pretty obvious that the one to work on, the more complex side, is the left side. Well, the only way I could combine these 2 fractions that are being added is if I had a common denominator, right? So now let me change colors. How can we get a common denominator? Well, isn't the common denominator just the product of these 2 things? I mean, I've got a cosine, I've got a 1 plus sign, so the left fraction needs a 1 plus sign, and the right fraction needs a cosine. And so we've done this before, not with trig things, but we've done this many times before. How can I get an extra 1 plus sign on the left? We can multiply top and bottom by 1 plus sine x. It's legal because we're multiplying top and bottom by the same thing, which is like a big fancy way of multiplying by 1, which keeps it unchanged. And the right one needs a cosine on the bottom. So here I'm going to multiply top and bottom by cosine x. So this is just, I mean, this is all algebra now. Okay? Well, now I've got a common denominator, and the common denominator is cosine times 1 plus sine x. See, here it is. There's my new common denominator right there. Now, what happened on the top? Well, on the left side, I had to multiply 1 plus sine times 1 plus sine. Remember, what happens when you square a binomial? You get the first number squared. 1 squared is 1. You get the second number squared. Sine times sine is sine squared x. And then you get 2 times the product of the 2. 1 times sine is sine x, and 2 of them gives me, you remember that it's like x squared plus, I'm trying to think, yeah, x plus y squared is x squared plus y squared, and in the middle you get 2xy. So it's just squaring a binomial. And then on the right side, well, that's just cosine times cosine, which is cosine squared. Okay, so all I did was some basic algebra, and I combined them into one big happy fraction with a common denominator. All right, now, can we simplify the top at all? You recognize something special about this part right here? Hopefully you see that's an identity. Yeah, that's 1. Sine squared plus cosine squared always equals 1. So that's just a big fat 1. And 1 plus the 1 over here would give me 2. Okay. And then I still have this middle term, 2 sine x. So now, just by combining this identity, I'm down to here. Okay. Got to do some scrolling, guys. So some scrolling. I've factored a 2 out of the top. Do you see how this thing right here has a 2 in both terms? So I pulled a 2 out. 2 times the quantity, 1 plus sine. Why did I do that? Oh, because there's a 1 plus sine x factor in the bottom too, and they can cancel. Cool. So now I'm just down to this. 2 over cosine. Well, isn't cosine the reciprocal of the secant? Hey, we got it. 2 secant x equals 2 secant x. And those are exclamation points just because of joy. Okay, so or in other words, smiley face, we have achieved our goal. So I would say what? You're probably getting the idea that this is 95% algebra now, which I know hasn't always been this class's strength. And, maybe I'm a little bit high, maybe 80% algebra and 20% knowing your identities. And then you got to wed them together, which is, that's how these things go. Again, let me take a little time out. I'm sorry. I'm just looking at your question yet, Kirsten, about secants being all over the place. It's an interesting way to describe it. I know you were talking about the last problem. Questions? Let's look at one more. This might not be the right one. Let me see. That one we already looked at. Just trying to find another good one here. Now, these are the other ones I've just taken a peek at are. Let me just show you a little bit. All I wanted to get across to you is proving identities is algebra and knowing your identities. And we just did, 3 examples of that. And as long as you get that concept, I mean, we can't reteach algebra right now, but you should be able, hopefully most of you can see that all I was doing was bringing identities together with normal algebra. All right, I wanted to show you a little bit about graphing. Just kind of and this is more of a summary. So you see we have an animation here. We've got the unit circle on the left. Well, that's interesting. Oh yeah, it's just showing you how, yeah, that maybe doesn't help a whole lot. But let's just wait. Maybe it's the next one. This is one way of looking at it. You know, in the first quadrant, sine is what? Starts at 0, and it increases up to 1. Okay, that's what happens from this point right here up to this point. Sine starts at 0, and it goes up to 1. And then in the second quadrant, it goes from 1 back down to 0 again at pi. And then third quadrant is the first time it goes negative, so it dips down and heads down at 270 degrees, down to -1. And then finally, it comes back up to 0, and it just repeats over and over and over, and you get this forever wave function. Cosine, I've told you before. Well, yeah, here's maybe a little bit better. And by the way, just forget about the numbers on the left. I had to make it that way so you could see the wave. But again, when we start over here, it starts at 0, heads up to its maximum, and 1.57, that's the decimal form of 90 degrees. And then that's radians. 1.57 radians is 90 degrees. And then it decreases down to 0 at 180 degrees, or pi radians. The same thing. Okay, now look at the cosine. The cosine is the same shape, except you see it doesn't start at 0, it starts at 1. And you knew that if you look at your charts. What's the cosine of 0 degrees? It's 1. And then in the first quadrant, what does cosine do? It decreases. See it going downhill here? It's going downhill. It decreases, and it keeps decreasing in the second quadrant. And then finally, when we get down to the bottom here, now cosine starts increasing. I'm missing a little bit with my arrows, and it comes up to a maximum here, and then starting over at 2 pi, it starts going down again, and it repeats, and it repeats, and it repeats. It's just kind of neat to see it all put together in one graph. And the cool thing is cosine and sine are perfectly congruent to each other. If you slid one graph over the other, they would match up perfectly. Just that one starts 90 degrees ahead of the other one. And then let me show you a little bit about the tangent. Okay, I've already got it graphed, so you'll have to excuse me. But if you have your charts handy, maybe have that handy. Let's start right here at 0 degrees. At 0 degrees, the tangent is 0. So the height of the curve at 0 degrees is 0. Then it increases. It increases wildly. Remember in class we did what's the tangent of 89 degrees? And I think we got something like 57, and we did 89.9, and it was like, it's getting huge. It's going up here. It just gets huge. But as soon as you hit 90 degrees, my dash line indicates it never will be there. That's an asymptote. It just like disappears. It's gone. And on our charts, what does that read? UND. Yeah, undefined. But then if you just go past 90 degrees, it reappears way down here at negative infinity. And it increases, it increases, it increases. And at 180 degrees, it's 0. And then it keeps increasing. And as soon as it gets to 270, vanishing act again. And then, so you see how tangent is forever going uphill here? And it does these vanishing acts when it reaches the vertical axis. So, beautiful repeating symmetry of the tangent curve. It's just kind of cool to see it all come together. This is an animation of the same. The only thing I don't like is it draws in the asymptote, and it shouldn't. So, you know, this vertical line shouldn't really be there, okay? There is no tangent at that point. Likewise, on the second wave over here, when it gets there, there is no line here either. So, but I mean, it's smoother, and you can see it connected to the unit circle over here. You see how it's tied together? So it does a nice job of showing what we were doing with the unit circle. So anyway, so again, what does the tangent curve look like? It's this repeating, increasing function that, you know, there were a lot more things we could have done with graphs, but, well, we just ran out of time in the semester, so. All right, so mostly today, what did we do? Well, we again took our 8 basic identities, and this time we made use of them and algebra to show that that we had some new trigonometric identities. We proved that they really were identities by proving that the left side was the same as the right side. And primarily we used algebra to do that. We took just a little peek into when you put this all together on the sine, the cosine, and the tangent graphs. And guess that's kind of the thought we're going to end our new material this semester on. Could we do one with square root signs? Do one what with square root signs? You mean an identity with square root signs? Do you have yes, but? Okay. I'm not sure. Do you have any that you any particular one in mind, Geneva? we could maybe save a little time. Oh, I know your voice is weak, but whatever. Geneva, by the way, was in 4 concerts this weekend, so her voice is close to it's needing a rest. So Geneva, just let me ask one more time. Did you have a particular problem in mind? No. I don't either. And normally you don't. I mean, we could have one that, let's see. Yeah, I may have to think real hard. You usually don't see that in these trig identities, but I'll tell you what, I'll try to come up with one that we could use tomorrow and spend just a few minutes on it, even though it's review, it's review day. So I'll try to come. Yeah, that's a good question, but it's not. It doesn't usually come up. And I'd only introduce proving identities to you guys. So I'll be honest. I can't ask you I can only ask you fairly basic identity questions on the final. I've already gone a little bit beyond that with the examples I went through today. But it's a really good question. Thank you. Other questions from all of you? Brandon, are you all right today? I feel empty. I haven't heard your voice yet.
Oh, sorry about that.
Hey, he's alive.
How you doing?
I'm fine. How are you?
I'm doing all right.
Yeah, just the way we started a little different, I didn't get to see any of you and you didn't get to see me, and
right.
Almost feels a little fake, but all right, guys, I think we're going to hang it up. I will tell you this, it might take me a little longer to post the video today because I'm going to have to edit it. The weird way I started today, it started recording like 20 minutes before we actually began, so I got to trim off so you're not staring at a still screen and hearing me count off 10 minutes to go and stuff like that. But it should be posted, let's say, in about 20 minutes to a half hour. Thanks. I look forward to seeing all of you tomorrow. Geneva, I hope your voice heals somewhat. Thanks, everybody.
Thank you.